सर को कॉल करो कि वो इंट्रोड्यूस करें। आप इंट्रोड्यूस करो, आप लोग इंट्रोड्यूस करो अपने वाले से, नहीं करो।
So, hello. I'm sure I'm audible. So, it's time to move on.
Okay, Dr. Jitendra.
Yes, sir.
First, allow me to introduce you to the participant. So, it's my immense pleasure to introduce Jitendra Goyal. He is my PhD scholar and currently doing a wonderful job in BITS Mesra, Jaipur branch, and his research was especially in this blockchain technology and its security and healthcare. He has a very vast experience. He was a faculty of the Politica. He was the faculty of the CSC department of the MNIT, ad hoc faculty. I hope. Am I right, sir?
Yes, sir. Yes, sir.
And he has a very good publications in the international conference in general. He is still working in this healthcare security issues in chain, and he was my always supporting hand, and he is also supporting me in order to organize this community development program efficiently. I hope that participant will get the more valuable information related to that research work which he has done under my supervision, and that information will give you the exposures of the further research gap in areas where the good work can be done once that idea has been triggered. So any assistance pertaining to those type of the idea which you may have in your mind by going through this talk, please feel free to ask a question, and that would be very much helpful for you. So now I invite Dr. Goyal to deliver his talk.
Sir, thank you so much for your nice introduction, and it's very great opportunity for me to work with you and under your supervision. Always your supervision was very beneficial and helpful for me through the entire journey of my PhD. So thank you so much, sir. So now,
Please continue. Please continue.
yes, sir. Yes, sir. So today's talk is on for this session. The today's talk is on the role of blockchain technology in securing healthcare data. So I'll introduce about this title. in this how this blockchain technology help in securing the blockchain data, healthcare data, which is generated by the healthcare IoT devices. So there are multiple kind of devices and healthcare data which can be stored to the blockchain technology. So how we can secure this data using the blockchain technology? So we will see that what is the structure of the blockchain, how the data is transactions are initiated in the blockchain, and how this data is added to the blockchain. After that, next step will be the smart contract deployment, then compilation of the smart contract, and then testing, and then deployment to the blockchain. Then what are the basic challenges and issues, and what are the research gaps when storing the IoT and healthcare data to the blockchain technology. Then we'll discuss a framework for securing the IoT data using the blockchain technology. So there will be one case study how we have stored the data. So we have taken the Raspberry Pi as a data to capture the IoT data and healthcare data. So there are several sensors embedded on the Raspberry Pi for itself, and they captures the human healthcare data, and then we store that healthcare data to the blockchain technology. After that, what are the advantages of this proposed blockchain based IoT data model? So first we'll discuss like what is the blockchain technology. So blockchain technology is basically a decentralized technology where all the nodes are connected at a peer-to-peer level. Means this one is peer-to-peer, and all the nodes in the blockchain technology are at the same level. So there are the data is the multiple data is grouped into one block, and then the data is added to the blockchain. So as shown in diagram, at the leaf level of this tree, transaction 0, transaction 1, transaction 2, transaction 3, these are the data set. So we are storing any kind of data. Those are like all data storage in this blockchain technology in the form of transactions. So transaction 0, 1, 2, 3 are the transactions here, or the data set here. We have to calculate the hash of this data, and then root parent hash of this data, and then the Merkle root hash of this data. After that, we conclude the Merkle root tree of the entire data set. So what we store this transaction data plus Merkle root data in the blockchain itself. So blockchain contains transactions plus the hash of entire single hash of the entire data set, and also contains some uh, header field, that is parent hash block and nonce value, timestamp value. We will discuss what is the use of this parent hash block, nonce value, and the timestamp value. So this one is the structure of the blockchain block structure, where the header part contains block version, which blockchain version we are using. Previous block hash is the hash of the previous block. Timestamp at which time the block is mined, and bits basically defines the difficulty level of this blockchain. Nonce value is a 32-bit nonce value that is used to identify a specific kind of hash value. Means how much starting bits must be zero, that is defined by this nonce value. uh, After that, there will be Merkle tree root hash. So Merkle root tree hash is the hash of the entire transactions, and the second part of this block is as shown in diagram. The red color sign diagram is that there is transactions. So a block will contain multiple transactions and some header part field. So this one is the mining task of the blockchain technology. So how the mining is happen in the blockchain. So a first step at defines that there are multiple users. This blockchain model is applicable for any kind of data where we want to store the data to the blockchain. So this user 1, 2, 3, 4 up to n means there are multiple users who generates the data set. Either this data may be the financial data set, or it may be the IoT healthcare data set, it may be any voting system data set, or any kind of data set it may be. So all users means multiple users at a same level. So all this one is peer-to-peer technology. So all user will work at the same level. So they will generate the data set, and this data or the transactions will add it to the transaction pool, and this transaction pool is over the blockchain network. So all data will be, all transactions will be stored in this transaction pool. After that, in second phase, we will fetch out, means miners will fetch out the set of or a bunch of transactions, and then these miners validate the transactions. Third phase is to validate the transactions. What is the meaning of this validation of the transaction? The meaning of the validation of transaction is like if A initiates a transaction, like A is paying $50 to B, then A must have $50 in his account. So all the transaction must be validated. Either A has that much of amount or not, A is eligible to cast a vote or not, A has that type of rights or not. So these all the transactions are first validated by the miners, and after that miner will mine these transactions and will mine one block. Means after validation, the miner will mine a block. And what is the meaning of the mining? Mining of the transaction is like the miner will find a hash value, Markle root tree hash value, Markle root tree hash value specified with the number of zero, starting bits of number of zeros. As shown in diagram, all transactions will be the set of transactions. Miner will mine the Markle root hash with the varying the nonce value, and level will be the n bits. For example, if for a particular hash value, if starting 10 bits must be the zero, then varying with the hash value, varying the nonce value, we multiply change this nonce value, and after some change, after some occurrence of this task, iterative task, we will get a hash value where starting n bits will be the zero. So that will be the final block. So all miners simultaneously mines block, and who mines the block first will be added to the blockchain. So after mining of the block, that block will be broadcasted to all the miners. All miners will verify the set of transactions with the threshold value and with that nonce value. Is this calculated Markle root tree is correct or not? Is this is this satisfies the criteria of n bits or not? If both conditions meet, in that case only this block will be added to the blockchain. So as shown in diagram, after 8 step, after verification of the block, this block will be added to the blockchain. Here, as shown in here, the last block is block 260, and newly added block will be added to the next to this blockchain. So this one is this blockchain where each block contains some set of transactions with some header value. Okay, so we have discussed here that we have to calculate the hash value. So what is the meaning of this hash value in this blockchain? How we will change the nonce value, and we will discuss this hashing in the blockchain technology. So basically, in blockchain technology, basic hashing is like we give some input in variable length as a plain text and nonce value, although this nonce value is this part of this plain text. So combinedly there will be two input, one is plain text, second is nonce value. So we will feed up these two arguments to this hash function, and we'll find this has fixed length hash value. So hashing generates always any hashing function generates fixed length output. We fixed length output irrespective of the input length. So size may be anything. If we vary this nonce value, if we change slight change in this hash input value, then entire hash value will be changed. So there are several properties of this hashing function. So like as shown here, first one is pre-image resistant. This one is one-way function, is like uh, for any input data x, if we find the hash, so always the high digest value is basically the hash value. So with the help of the digest value, we can't calculate the x value. And second property is second pre-image resistant. So any party, it means like any party can't find a input hash for a specific output hash. And third property is collision resistant, in which two different inputs, one input is x input, second input is the y input. So for any two inputs, There should be, they cannot be find any output same hash output for two different inputs. So one property is like hashing is compression and expansion. Irrespective of, we have already discussed, like irrespective of the size of the input, the output has always be fixed. If we are using SHA-256 for example, generally SHA-256 is used in the blockchain technology. So irrespective of the size, if we take input size of 1024 bits, so output will be again 2 raised to 2 output will be of 256 bits. Either if, or we take 64 bits input, then output will be again 256 bits. So irrespective of the size, output is always same. There is one more example. Either we take any text format or we take any image value, output is always in length. For the input is a quick brown fox jumps over the lazy dog. So the size of this input is 43 bytes. And if we pass this input in the hashing function, that it calculates or it finds, it generates 256 bits. And if we take input as an image in as an input where the size is 96323 bytes, then again the output is in the same length. So irrespective of the size and irrespective of the type, the output is always in the fixed length. There is one more property, that is avalanche effect. So if there is minor change in the input, if there is any very slight change in the input, the output will be completely changed. So as shown in diagram, the input is like in first case input is 4 times 2. After applying the SHA-256 on this input, output is like 1 2 AE 3 2 and so on. And when we change last digit from 2 to 3, and again we applies the SHA-256, then output is 589 T2. That is completely different from the previous output. So if there is minimal change in the input, then output will be completely changed. So next property is determinism property. That is like for two different means, two different machines, and for same input, output will be always same. So for all for 4 times 2 on machine A, output is 1 to A. So this is a machine independent function. So so you can use any kind of machine for the mining purpose, or output will always be same. So as we have discussed pre-image resistant, like it's impossible to find out again as the output input from the given output. This one is always one-way function. Next property is collision resistant. We have already discussed here. For two different inputs, output will always be different for all inputs. So this one is basic evolution of SHA-256. So first, this SHA was introduced by NIST and NSA in 1993. After that, SHA-1 was introduced in 1995. This one was the revised version of this SHA-1. Then SHA-2 family was introduced in 2002. So keep in mind, SHA-256 is the function of SHA-2 family. So SHA-256, SHA-384, SHA-512. These are the functions of the SHA-2 family. So in 2012, NIST again released one more family, that is SHA-3 family, and KACHEK is the function of this KACHEK. KACHEK is the function of this SHA-3 family that is generally used in the Ethereum. Ethereum is one more. We will discuss what is the Ethereum, how it works. So KACHEK is generally widely used in this Ethereum, that is again hash function. So output length is in 256 bits. So and for SHA-256, there are 64 rounds to calculate the final hash value. So one message block size for SHA-256 512 blocks, and there are 32 words, 32 bits each word, and number of bits are 8. So there are total 64 rounds. For each round, we will take 1K constant for each round. So the application of SHA 256 are generally we use this SHA or any kind of HASI function for data integrity. What is data integrity? Like we download any software and then there hash of that data is added to this data, and again after download of the data we calculate again the hash of that data. If both hash are exactly same, then we can state that this data is not modified and not altered. And this hash function or this SHA-256 also used for the non-repetition and also for the digital signature. So if any party generates a hash function with his key, then he can't deny that I didn't generate this data, because this key of that user is associated with this data part. So this SHA is again widely used in this blockchain also. In mining purpose, we have to vary this nonce value and calculate iteratively Markle root tree. Then this one is where the hashing is used, and for making it chaining to the previous block, again we use the hashing. So in blockchain at two places we use this hashing function. So here as shown in diagram, first hashing is in block. As shown in diagram, there are three blocks: block header n-1, block header n, and block header n+1. So block n contains hash of the previous block. This one is the chaining of the block. This here hashing is the used to provide the chaining to the previous block. Second hashing is at the from body part to the header part. So we calculate the Markle root tree, and to calculation of the Markle root tree itself again contains multiple hashing processes. There is a tree structured hashing processes. So again we calculate the hashing of all the transactions. So in blockchain, there are at each block, two times hashing will be calculated. In Markle root tree, uh, there are multiple hashing functions. For each two leaf nodes, we combine these two leaf nodes, and then again we calculate the hash function as shown in this earlier diagram. Like so for all transactions, we calculate hash 0 and hash 1 for transaction 0 and 1. Then again, the root hash will be calculated. Then again, for two hashes, and then again, root hash will be calculated, parent hash will be calculated, and again, so the structure will go up. Uh, so, so there are multiple transactions. We calculate the hash of each transaction, and then the parent hash will be calculated. This one is the Markle root hash tree function. So who will mine the block? So basically, who has the higher computation power, who will has the higher probability to mine the block. So like hashing is a resource extensive task. So to obtain a desired hash value, we have to alter the nonce value, and every time we have to calculate the hash. So the transaction size is of the total transaction size is 1 MB. So we calculate the hash value. Who has the higher probability, who has the higher computation, will get the chance to mine the block. And the luck is also there, that you may get that chance in first attempt also, or you may get the chance in you it is also possible that you will not get any chance to mine to find out that exact value of the nonce value, so that you can obtain the desired level of Markle root tree. So efforts and luck both will work here. So next is like a proposed framework for securing healthcare IoT data using the blockchain technology. So this one is like how we generate, how we secure the data, uh, using the blockchain technology. Here we are considering IoT data, healthcare IoT data. So this one is also called as MIoTs, medical IoTs or healthcare IoTs. So this model is applicable for any kind of IoT data. It may be a supply chain management based IoT model, or it may be like any financial transaction or any kind of model. We can use this model. So for those cases, the input data will be differ from for our model, but the deployment, compilation, and all tasks will be same. So here what happens is like all the parties initiates the transactions. We club all the transaction and then add this data to the blockchain. So this blockchain is distributed to the nodes. This entire blockchain, this one is distributed and decentralized technology. This blockchain is distributed. The two words, distributed and decentralized. So distributed means the data is distributed to all the nodes. Each node contains its own copy of entire blockchain. And decentralized means there is no centralized authority to control the software or the technology of this blockchain. Each and every node has the standard piece of software of this blockchain. So this control is decentralized. So when a block, so what is the block? Block is the bunch of transaction, and this bunch of transaction is added to the blockchain. So first the transaction is initiated. So with the help of any, there is one plugin, that is MetaMask, that provides us a interface to initiate our transaction to the blockchain. So we have our account on this MetaMask. This MetaMask is plugged into the Chrome browser, or Chrome. With the help of, we can add this MetaMask as a plugin to our browser, and then we initiate we initiate our transaction with the help of this MetaMask. This MetaMask signs the transaction and then add this transaction to the Ethereum blockchain. So adding this transaction, again there will be all the steps we have earlier discussed, all the mining steps. All the mining steps means will like, first all the transactions will be captured to the transaction pool, and then a bunch of transaction will be fetched from this transaction pool to the all the miners. Then they will mine a specific level of hashing value, specific desired level of hash value. If starting number of zeros will meet the desired level, then that block will be added to the blockchain technology. So this and finally that block will be added. So in Ethereum also, there this Ethereum is basically platform and one application of the blockchain technology. Basically this Ethereum is application, but it also provides a platform to add us to our own smart contract to the blockchain. What is the smart contract? When we discuss this blockchain in Bitcoin, so in Bitcoin, what is Bitcoin? Bitcoin is like, there is the software is only to used for the financial transactions only. We can't define our own piece of code, and we can't use it for other purposes. But in Ethereum, we can write our own software, we can write our own program that is called as the smart contract. So this one is kind of a legal agreement, and that is written by the developer or the programmer, and then this smart contract is added to the blockchain, and this blockchain is spread to all the nodes. So when any transaction is initiated that communicates with a specific smart contract, then respective action will be triggered. Like when we consider a example of e-voting system, and there is one software, when there is one smart contract of the voting system, where we write multiple user will register themselves and then will cast their vote, and then after a specific time period the result will be declared. So all the users will initiate the transactions. All the users will initiate the transactions. The transaction will contain the vote of the user, and these votes will be stored to the blockchain. No one can alter these transactions, and after a specific time, if dedicated or a fixed function will be called, and then that function will declare the result. So this one is the triggering in the database. So we can use this is blockchain in e-voting systems, supply chain management, also in certificate generation. So there are lots of applications of the blockchain that can be written in the Ethereum, and these applications are known as the smart contract. So how to write the smart contract, what language is used to the smart contract, and how to add the smart contract. So basically, to write a smart contract, we use the Solidity language. So Solidity language is the language to write the smart contract in the Ethereum. So there are multiple platforms in which we can write our smart contract. For Ethereum, Solidity used. So there are multiple other platforms like IOTA. There is Polkadot. There is Hyperledger, where other different development programming languages are used, like Move and so on. So we write our smart contract, and similarly we compile our smart contract. So two types of files are generated. First one is the bytecode, and second one is the ABI file. So what is the bytecode and what is the ABI file? So bytecode is the compiled code of our smart contract that is deployed to the blockchain. Or here we are discussing about the Ethereum blockchain. So here we are discussing about the Ethereum blockchain. So this bytecode is added to the Ethereum blockchain itself, that is written in the Solidity language. After compilation, blockchain this bytecode will be deployed to the Ethereum. And there is one more part, that is ABI file, application binary interface. So this ABI file is used to communicate with this deployed smart contract. We will see how this ABI is helpful to interact with this bytecode. So this one is one sample code of health data. This one is sample Solidity code that is used to store the health data to the blockchain. So what we have done here, there is one contract named health. There are two variables. So basically this what we are doing here is we are just storing the pulse rate of a person and SpO2 value of a person. So for the storing these two variables, we need two functions. First one is to set the data, second one is to set the to get the data. So for pulse, to set the pulse, we have function set pulse, and to fetch the data pulse, we have the function get pulse. And again we have the function SpO2, set SpO2 to store the SpO2 value, and to fetch the SpO2 value we use the get SpO2 function. So these set get functions are public in nature, are the view types. And so we will discuss in how we write the Solidity code in early in next lecture, or maybe in a second or third day. So how to write this smart Solidity code, what are the data types used, what are the functions, how to write these functions, and so on. So this one is basic sample code to store SpO2 and pulse to the blockchain. So we take two inputs and store these parameters to the blockchain. So first we write this smart contract in the Solidity language. The extension is here .sol. This one is extension for the Solidity. And then we compile the smart contract and we deploy the smart contract to so we do ABI to interact with this deployed. So the front end from which we will communicate with the smart contract. So there is one online IDE named Remix IDE, that is basic. This Remix IDE is slightly easier with compared to manually installing the Solidity compiler. So generally for testing purpose we use this IDE compiler. You may use your own any kind of ID to you use any another compiler to compile the smart contract. So this remix ID, the URL is like remix.ethereum.org, in which you may write your own smart contract, and with the help of the browser itself, you can compile your own smart contract. So this one is open source. So I so you have to write your smart contract, and you can directly compile this smart contract to the blockchain. So there are you have to and then as shown here, uh, so as shown here, this one is a MetaMask plugin. Okay, these are the accounts from any. We have multiple accounts. We can use any account to compile our smart contract and to deploy our smart contract. So this one is for compilation. For compilation, we will use this compilation tab, and for this deployment purpose, we will use this deployment phase. So gas limit is how much gas we are willing to. So in blockchain, so in blockchain, uh, 1 minute please. Uh, so in blockchain, and when we initiate any transaction, is that is okay. So in blockchain, when we initiate any transaction, then we have to pay some fees. So in blockchain, every transaction is paid. So how much fee we are willing to pay, we will define in this gas limit. And we will define also value. If our function is taking some value for any transaction deployment, or for any transaction initiation or for any transfer. So we can deploy our smart contract, we can deploy our smart contract with the help of this remix ID. So one blockchain may contain multiple smart contracts. So we will have our own smart contract. Another user may initiated his own smart contract. So there will be multiple applications also named smart contract, or also we can called it as we can also call it as a smart contract instance. So one user may contain multiple accounts. So what is account in the blockchain technology? Next thing. So account is like when any user initiate a transaction in mining phase. When any user initiate a transaction, then this transaction is um, added to the blockchain. So first, the user must has its own address from which he is initiating the transaction. So this address is generated with the help of this private key of the user. So this user will contain his own private key, respective public key, and his address. So a user may contain multiple accounts. Each account will contain a pair of public and private key and his address. So a user may use his any account address for initiation of the transaction. So there is a Ganas as shown here, uh, as shown in diagram. After compilation of the smart contract, we obtain two files, bytecode and ABI. Bytecode is added to the blockchain. This Ganas provides us the instance of the we when we deploy the smart contract, then a contract instance is created to the blockchain, and with the help of this Ganas, means Ganas again provides a complete framework in which we can deploy a smart contract and we can communicate with the smart contract. So in this diagram, we have deployed our smart contract to the Ganas platform, and contract instance will be there. Then with the help of ABI file, and there will be Web3 that will help us to communicate with the deployed smart contract. So Web3 technology is generally used in the front end to communicate with the any kind of distributed application. So we use Web3 for the communication, and ABI provides us the interface to communicate with the smart contract. Again, the Web3.js is used. So Ethereum in Ethereum network. So Ethereum is basically public blockchain network. So here again the word is public blockchain. So there are two. There are private blockchain, public blockchain, and hybrid blockchain. So public blockchain means any party. Public blockchain means any party can join the blockchain network, and any party can initiate a transaction. Any party can view the blockchain transaction. In private blockchain, only authorized user only authorized user can access the blockchain network, can initiate only authorized user can initiate the transaction, only authorized user can mine the transaction. So there is difference between public and private blockchain. So private blockchain is more likely towards the centralized architecture, whereas public blockchain is completely decentralized in nature. So there are several other models like hybrid blockchain or consortium blockchain. So for consortium blockchain, that blockchain is basically for a particular organization that contains that organization. For example, a organization contain 2,000 nodes. These nodes are basically users or the miners. So within that organization, that will be public. So a member of that organization may join the blockchain network and may participate in the blockchain. So for a that particular organization or particular consortium, that blockchain will be the public, but outside that consortium or organization, that blockchain will be the private. So this node are the group of users or the miners. So a node may contain. We have already discussed that each and every node contains its own copy. So that node may contain either a full copy or a light copy. So full copy means that node contains each and every transaction and the hash value, Markle root tree of that block, and each and every entry of the block. But in light copy of the blockchain, where the only the header part is managed, some blocks are used. So working with the light blockchain, light copy of the blockchain is easier to maintain. So each node runs its own client. So own client, each node participate in the mining process. It's not mandatory to participate each node. It's not mandatory to participate in the mining, but each node can participate in the mining. That is publicly open. If any node want to mine a block, then he can participate in the mining. And if a node finds a correct hash value, then he will get the reward. And how the reward will be generated? So the reward will be generated from the blockchain model itself, and also there will be some transaction fees that will be paid to the miner. So Web3.js is used to deploy the smart contract to the blockchain, and with the help of MetaMask and any front-end application, we can communicate with the blockchain architect. We can communicate with the blockchain model. So our blockchain model will contain the smart contract or the instance of the contract. We will communicate with that instance of the contract. So this one is Ethereum blockchain structure. So this one is Ethereum blockchain structure, where each block contains multiple fields, So there will be two types of roots in the in Ethereum blockchain: transaction root, state root, and receipt root. So transaction root is the Merkle root of each data is stored to the transaction root. So state root is generally this Ethereum is called as the Turing complete state machine. So Turing complete means if any task is solved by any Turing machine, then Ethereum is also capable to find out that solution. Means any problem that is solved by the Turing machine, that also can be solved by Ethereum machine. So Ethereum machine or Ethereum virtual machine, generally called as EVM or Ethereum virtual machine. So any task that can be solved by Turing machine, that can also be solved by Ethereum virtual machine. So if we initiate a transaction and that transaction is added to the blockchain, so for that particular contract instance, the state will be changed. So particular, if we add any data to the, but if we are generating, if for any example of healthcare data, so current pulse rate is 72, and after 10 minutes we add one more data, that current pulse rate is 76. So the state has been changed. So the current state will be managed by this state rise, and the state root will be calculated. So Ethereum is kind of state machine that is Turing complete. So transaction for each transaction root will be calculated. For each state, the state root will be calculated. Okay. So again, similarly, there will be a receipt root. So after verification of the transaction, and what's the respective outcome of that transaction, that will be stored to the receipt root. And this one is the part of this this is the structure of this Ethereum blockchain. So internal structure may vary in Ethereum, in Bitcoin, in IOTA. So internal structure may vary according to the requirement of the blockchain. So Ethereum is application, but blockchain is one technology. So this Ethereum, Bitcoin, these are the applications based on the Ethereum. Ethereum, Bitcoin, IOTA. These are the applications based on the blockchain technology. Okay, so this one is again transaction root, state root. So we have discussed that Kachak 256 is the hashing function of the SHA-3 family, and the state root is calculated uh, when there is any change in the state of any contract instance. And similarly, the transaction nonce value, gas limit, all will be the part of the transaction. We will vary the nonce value, we will set the gas price, we will set the gas limit, from which value we for which uh, uh, for from which address we are initiating the transactions. Though a transaction will contain multiple header value, and there will be Merkle root tree that will be stored to the transaction root. And Ethereum block will contain the hash of the previous block, transaction root, block number, timestamp, difficulty level, etc. So this one is the MetaMask. So how to work with the MetaMask? So MetaMask, as shown here, this one is the plugin of the MetaMask. Uh, Extension is added to this Chrome browser. So this account contains 37 Ethereum. Okay, so this one is a Ringby text net. This one is for Ringby test network. So you may choose your own any kind of test network. There are multiple test networks in nowadays. There is Sepolia test network. There is Robston test network. There is Ringby. Ringby has been closed nowadays, but Robston and Sepolia is also working here. So you may use any test network. So what is the meaning of this test network? So and how it's different from the mainnet? So test network is basically when we add any transaction, we have discussed that when we add any transaction to the blockchain, then we have to pay the fees for each and every transaction. So if initiate a transaction in the mainnet, in that case we have to pay fees for each transaction. But when we are when we are testing or developing our model, so for testing purpose we need the test, we are not able to pay, if we are not able to pay the cost for each testing phase, so we may use the testing network in which the cost of the transaction will be in the dummy ethers or virtual ethers. These ethers are valid for the for a particular test network. If I am using the ringb test network, then I have to earn first ringb ethers. If I am using sepolia test network, then I have to earn the sepolia test network. So how to earn these ethers? So there are multiple faucets. From with the help of these faucets you can earn the uh, dummy ethers for the test network, and these ethers will help you to initiate the transactions. So as shown here in diagram, uh, uh, ethers are deposited to the blockchain, and we can earn the ether from several faucets. And for with the help of our account, this account contains our account address, public key and private key, from which we initiate the transactions. Okay, so as shown here, there are mainnet. Ethereum mainnet is original Ethereum network in which for initiation of the transaction we have to pay the transaction fees in real ether. And there are multiple test networks: Rapston, Covin, Ringb, Gorilla. So these are test networks. We can There is one localhost 8545. So what is it mean is like in our system or in our desktop device itself, we can design our own test network that will run on our system. So Gath is one tool which provides us platform to run our own blockchain to our own system. So we have to start the server with the 8545, and then using this Gath server, we can initiate the transaction and then store that transaction to the our Gath model. So for with the help of our account address, we can initiate transaction with any Ethereum network. So but for each network we have that kind of ether. If we are using Ropsten, then we will need the Rapston ether. We use Covin, then we need Covin ether. If we use Mainnet, then we will need the Man ether. Mainnet ether means original Ethereum platform. The user may contain multiple account addresses, and each account will contain that again three fields: public, a pair of public and private key, and the account address. So for as shown here, there is one external. There are two types of accounts in the Ethereum blockchain. First one is external account, and second is contract account. So external account address is the address of the user, whereas the contract account is the address of the contract at where the contract is stored. As shown here, as shown here in Ringb network, three contracts are stored. So at which location the contract is stored, that is the contract address, and the user from which the user initiating the transaction, that is the user account address. So why we need the contract account address? The reason is like, if first contract is initiated, that is related to the e-voting system, then next time we have to communicate with the e-voting system contract. So we need that contract account to which contract we have to communicate or we have to interact. So the next is supply chain management contract. Then again we need the address of that supply chain contract address. So we will communicate that supply chain management contract address, so on. So there will be contract address and there will be the externally account of the account address of the user. So next is this one is how to earn the ether. So actually this ringb network is there are this ringb network is deprecated. Now Sepolia is in working, so there again there will be pushed to earn the ethers to initiate the transactions in that network. So our next is like our model to storing the healthcare data to the blockchain. So I think that this diagram is completely not visible in this slide. So I have divided this diagram in three phases: left zoomed, center part, and right part. So this first is like this left side part, this one is center part, and this one is right side part. So first part, so this one is IoT sensors with the Raspberry Pi. This one is initiation of the transaction, and this one is the blockchain network. So left, this one is the view of the image with the zoomed format, that is left zoomed view. So there are multiple sensors are embedded to a person's body, where these are multiple sensors and associated on the person's body. So the sensors are either in analog sensors or it may be the digital sensor. If the sensors are analog sensor, if the sensors are analog sensor, then we have, and we are using Raspberry Pi, we may use the Arduino itself. But there is issue with the Arduino is that if we use Arduino, in that case we can't write we can't use our node as a mining device. So using our Raspberry Pi in the mining, we use because Pi provides us the capability to write to deploy the smart contract, and this Raspberry Pi can also be participate in the mining. But Arduino is not capable to do the mining task, and the libraries are also not available. So Raspberry Pi is a digital device, so that takes the input in the digital format. This LM35, AD8232, ADXL335 pulse sensor, these are the analog sensors. So first we have to convert these analog signal to the digital signal with the help of this MCP3208 ADC. This converts analog to digital, and we feed this data to the Raspberry Pi. If we already have the digital sensors, then there is no need to convert this digital data to the convert we directly we can feed this digital data to the Raspberry Pi. Okay, so all healthcare data, IoT data, will be captured and will be fed to the Raspberry Pi. Then Raspberry Pi will initiate the transaction. This Raspberry Pi again then initiate the initiate the transaction. Initiate the transaction means store these data to the blockchain. So storing any kind of data again here will be treated as the transaction. So this Raspberry Pi is connected with the internet. This one is center view. So uh, this data we will use the Infura API, because we have discussed that uh, there will be in a blockchain network there are multiple nodes. Each node can initiate the transaction and each node can participate in the mining. So each node can initiate the transaction. So we here we have to be work as a node. So how we participate in the node? So Infura is one portal that provides us the API to initiate the transaction. So with the Infura we will generate the API, and then we will use this Infura to initiate the transaction, where we will work as the Infura node of that particular network. So we will initiate the transaction with the Infura node, and this Infura node will be work as a part of entire blockchain. And with the help of this Web3, we will feed this data to the blockchain. So we will need our account address. User must has its own account address to initiate the transaction. So this one is right view. Here the here we will use our account address to initiate the transaction. So to which contract we have to communicate? We have to communicate a contract instance that is of particularly to store or to manage our IoT data. So as in shown in diagram, this contract instance is the contract instance of medical, a software or a solidity code of storing the IoT data to the blockchain that is already deployed after compilation of this, that is already deployed. So first we will compile our smart contract, means developer will compile the IoT healthcare model to store the data to the blockchain. So that he will compile the smart contract and will deploy the instance of the smart contract to the blockchain, and a user will communicate with the instance of the smart contract. Okay, so the transaction will be initiated with this account and will be stored to this contract instance. So again there will be state root, there will be transaction root. Okay, so transaction root will be changed, means updated, and state root will be updated because state has been changed now. After each and every transaction, the state will be updated. All transaction is also updated, but the state is again updated because now our model is jumped to the next state. So always we can consider this Ethereum as a state machine. That is like in theory of computation, there is state machine. When we give some input to a state, then we jump to the next state. Similarly, when we are in Ethereum, we are in on the state X. When we give some input to the state X, then the next state will be the Y state. So similarly, this one is again the state machine. So this one is data collection from IoT sensors, from sensors, IoT sensors to the Raspberry Pi, and then feeding the data to the blockchain. So this one is the activity diagram for storing the IoT data to the blockchain. So as shown here, there are three parts. First one is where the user will initiate the transaction. Second part is uh, developer or manager part, in which a code or a smart contract is added to the blockchain. Third part will be the Ethereum blockchain. So first so first is like 1 minute please. So first part is that is patient side, from where we feed the data to the blockchain. Second part is the deployment of the smart contract, and third part is Ethereum blockchain. Okay, so in middle part, or that is a developer part or manager part, where a smart contract is designed. Smart contract design means we have to write the smart contract in the Solidity language according to our requirement. We test the smart contract. If the smart contract is correct, then we deploy this, we compile the smart contract. After compilation, two files will be generated, ABI and bytecode. Then bytecode will be deployed to the blockchain. So blockchain phase is in the third column, that is Ethereum blockchain. So deployed smart contract will be added to the any block. It may be n-1 block, n block, or n+1, or n-6, 7. So any earlier block, the block will be in the current working block, the smart contract will be deployed. After that, a user will initiate the transaction. Initiate the transaction means there will be multiple sensors on the patient's body that will capture the data. This captured data will be fed to the blockchain with the help of either Raspberry Pi, or you may use any uh, desktop system to feed this data. But the benefit to use the Raspberry Pi is portable and consumes very less energy, so that can be embedded near to the patient body itself. Okay, so we can store the data with the either Raspberry Pi or any another computer system, so that data will be added to the current working block. So as shown here, the smart contract is added to the block n minus 1, and the current working block is n plus 1. Okay, so so current working block is n plus 1. So the state of the n minus 1 block at where the contract is stored, the instance of that contract is stored, will be updated. Okay, so state of this the state of this contract instance will be updated, and transaction will be stored to the current working block. Current working block means this transaction will be added to the pool of the transactions, and then there will be again the mining phase. All miners will fetch the transactions. When this transaction, the bunch of transactions will be mined, then that block will be added to the blockchain. Okay, so I need 10 minutes, 5 minutes break if you are comfortable with this. I will be there after 5 minutes only.
We are taking a short 5 minute break. We will continue after 5 minutes.
Yes. Size of the, okay, I got that diagram. I have so actually there is one instruction like the diagram to be enlarged, difficult to read. Okay, so I will check out that also. So this diagram, na? So is this okay? Actually, you all are mute, I think so. I'm not able to get the feedback from you. Okay, so this one is like okay. So one more thing, if is this going comfortably with you, or if you need any, like if the speed is slow or fast, we can change according to your requirement. Okay, should I continue or any suggestion? Okay then. Okay, so this one is like this model is in this model is okay. So first one is IoT. There, this model is again in three stages. First one is storing the data from IoT sensor to the blockchain. But before this, the model or the smart contract has to be deployed to the blockchain. So for at any instance, the smart contract will be added to the blockchain, and after that, the data will be added to the blockchain. Okay, so respectively state will be updated, and respectively transaction will be added to the new block. Okay, so this one is wearable health IoT device setup. So this one is setup of the IoT device to capture the data. Now listen, either you can use IoT model, or you may use any image which you want to store to the blockchain itself. Okay, so this not necessary to always use the healthcare IoT devices. If you are capturing the data and from any computer system, then you can use that data also. But this model is we are discussing a healthcare model, medical IoT healthcare model. Okay, so our purpose is to capture the data and to store that data to the blockchain. Okay, so data may be in any format or any type of data. Either it may be temperature, it may be heart rate, or it may be a it may be a ECG data. It may be also in image form. If there is a X-ray image, or there may be a cell image. But for cell image or X-ray image, we have to first convert that data to the text format, and then we will feed that data to the blockchain. Okay, and similarly, there will be smart contract. There will be first phase will be design of the smart contract, then compilation of the smart contract. After testing the smart contract, we will deploy the smart contract to the blockchain. Okay, okay, so our next is so so there are several challenges when we use blockchain based IoT model. Okay, so first challenge is like physical security of the IoT device. One side we are discussing that we have to secure our data. We have to secure our data. We have to secure our data. Okay, other side, the IoT device, physical security of the IoT device again is the major challenge. That can be hacked, then can be captured, that can again that can capture inaccurate data. Okay, so the security of the data is the first challenge. Second challenge is immutable ledger. So immutable ledger, we have discussed that once the data is stored to the blockchain, can't be altered. Okay, and for example, if that sensor captured the wrong data, like if we are using pulse sensor, that is attached to our body, and due to the misplacement of that sensor, that is capturing the wrong data. Okay, so once the data is captured with these IoT devices, that can't be altered. Okay, that is one more challenge in this IoT based model. Then accuracy of the IoT sensor is again one challenge. Like we have to calibrate our IoT sensors. So this IoT sensors must be the industry grade sensors, where the reading of the sensor must be accurate, or they must be properly calibrated so that they read the value in proper output. Like if we are using the ECG sensors and we are supplying power supply to the ECG sensor that is low, then the entire ECG waveform will be downside to the actual reading. Okay, so all IoT devices must be properly calibrated and must be of the industry grade, and the placement of the sensor must be the accurate. Okay, and physical security of the IoT sensors should not be the compromised. Okay, so there are multiple sensors we are using here, that is LM35, DS18D20, MAX 30100 pulse sensor, and so AD8232. So there are several other sensors available in the market itself. these sensors these sensors are just only for testing purpose. We can't discuss here the accuracy of these sensors, because that is again the separate domain. There will be the electronics part, that sensor is taking the correct reading or so on. So we will not discuss the accuracy of the sensors. These we will just considering that these sensors captures the exact value, or these sensors are placed at the accurate location. Because when we place the ECG sensor on the human body, the placement of the ECG sensors also plays a major role in the data capturing, during the data capturing. So this one is the pulse sensor that is embedded to the either the fingertip or the earlobe. So this one is based on the photoelectric method. So there is one rays that is transmitted from this device, and that passes through the blood vessel, and the oxygenated blood travels through these vessels. And again, the when after the reflection of that rays will be detected with the photo detector. So by using this pulse sensor, the pulse is sensed. So every beat of the heart, the oxygenated blood will pump to the vessels. So this one is the technology behind this pulse sensor. We are not bothered about how this pulse sensor exactly works as the ratio of the pulse sensor here. We are considering here as there is one pulse sensor that is just capturing the pulse sensor of a human body. Okay, so this one is the working of the pulse sensor. uh, Heart pumps the blood that supplies the oxygen to the hemoglobin, that through the arteries that travels to entire body and through to the earlobes and the fingertips. We use the device from which we use the body part from which the rays will reflect and transmit it. So earlobes and fingertips are the suitable locations, and again that is the part of the medical industry. Okay, so this one is the ECG sensor we have used here. So this ECG sensor, this one is the device that is embedded to the Raspberry Pi, and that captures that captures the ECG waveform of the human. So this one is the physical specification of the AD8232 ECG sensor. This one is 3 electrode ECG sensor. Again, I am saying this one is only for testing purpose, because in real time, generally we use 8 electrodes or 12 electrode pins, but we are using a 3 electrode system. So these are the physical specifications, a working temperature of these sensors, and so on. Okay, so how this ECG waveform works, when there will be three part: P wave, QRS wave, and T wave. Okay, so activation of arteria part, when activation of the arteria part, P wave is generated. When the activation of the ventricular part, the QRS wave is generated. Then during the recovery wave, T wave is generated. So this one is the basic structure of the ECG waveform. Okay, so uh, there will be arterial systolysis, ventricular diastole, and T wave will indicate the ventricular repolarization of or the recovery waveform also. So there will be different interval between P and R waveform. PR interval will be there. ST segment will be there, QRS complex will be there. The amplitude, again, the amplitude of this QRS will also be there. So there will be a complete waveform, and there should be one person. There should be one person who helps to deploy the smart contract. There should be one medical person who can easily identify this waveform and can give us the feedback so that we can write our smart contract accordingly. Okay, so what is the length of this PR waveform, what is the length of this QRS waveform, and so on. Okay, after analyzing this waveform, after analysis of proper analysis of this one is our testing model. So we didn't use any medical stream person for the analysis of this waveform. Okay, this one is standard idle time between PR interval should be the 0.12 seconds to the 0.22 seconds. QRS waveform should be less than 0.12. QT waveform should be less than 45, 0.45 seconds for men, and for 47 seconds for the woman. Okay, so these one are the wave interval time, ideal wave interval time. If there is any change, either time is shorter or the higher, so that point has to be identified. Okay, so this one is Raspberry Pi setup, where this one is MCP3008. That is again analog to digital sensor. This one is electrode, three electrode. This one is electrode connected. We place three electrodes, we place three electrodes on the human body. So again the placement matters. Again the placement of these electrode matters. Okay, and that is again defined by that is again set up by a expert of the medical science with the approval of medical. Okay, so these sensors, these electrodes are connected to the electrode connectors. This one is A2 AD8232 heart monitor, and there will be power supply, there will be ground voltage, there will be output. Okay, so ground is ground, there is no issue with this ground, but there is 3.3 volt. So this voltage must be exact 3.3 volt. You must ensure that if you feed higher power supply, then the output of this waveform will be, the amplitude of this waveform will be higher. If you give the lower voltage input, then the amplitude of this waveform will be go down. Okay, so these values must be checked and set with the expert. Okay, and after this collection of this data from AD to analog to digital converter, this one is IC from analog to digital converter. Okay, okay, so there will be temperature sensor. Green is sorry, red is here denotes the power supply, black denotes the ground here. If sensor has three sensors, one is output, one is ground, and one is power supply. Similarly, two input, ground and power supply, one is for output. So each sensor contains three output. Just max 30100 contains one more output, that contains two output, SDA1 and SCL1. Okay, so Okay, so this one is our experimental setup. Okay, so we are feeding the data from, we are collecting the human data, healthcare data, with the help of any sensor, and storing to, with the help of Raspberry Pi, we are storing to the blockchain. So this one is the specification of a Raspberry Pi. So we have used here Raspberry Pi 4 Model B with the 8 GB RAM, 4 GB RAM, and this one is Cortex A72 ARM V8 processor with 64-bit architecture, and this one is quad core processor, and we have used Raspbian operating system, and we have used several sensors, one analog to digital converter, there is one GPOT and connectors and breadboard. Okay, so the biopotential signals along with the noise is captured with the sensor, and then with the help of converter, with the help of Raspberry Pi. So these data is work as transaction. Okay, so any kind of data that is generated with the any kind of data that is generated works as the transaction. Okay, so this transaction is initiated by the user, and what is the user? User is the node. That node will initiate a transaction that will be added to the pool, and then there will be a complete mining task, and then the data will be added to the blockchain. Okay, so as shown here, there will be one cardiologist. You may either use a cardiologist to analyze the ECG waveform, or you may write your own code. Means you may write a code with the help of any expertise in that domain, that will read the data and that will analyze the data and directly give you the output. So some data, we for that, for temperature we can state that after 10, if the temperature is 102 degree centigrade, then that is sorry, if the data is 102 degree, then that is high on the higher side, or if that is lower than 96 or 5. And so some basic data for basic sensor, we can give our prediction, or after some consulting with the expert, we can write our smart contract. But if that data or reading needs very expertise or very precise knowledge, then we will consult with the any medical expert person to analyze the data. Okay, so uh, for this AD8232 sensor, this MCP3008 is 10-bit sensor. So we are converting this signal to the 10 bits digital sensor. This entire value output, this one is analog signal, sorry, analog sensor. So that will generate the output range of from 0.0 to the 3.3 volt. Okay, so we have to divide this entire range to the 10 bits, because our sensor is of 10 bits, capable of handling the 10 bits. So 0 will be 8 times 0, and 3.3 will be the uh, 8 and 10 times 1. So this entire wave, that entire range will be quantified in the that entire range will be quantified. Okay, this one is one sample we have. Actually, for collection of the data, the human must be properly laid on the bed, or the placement should be properly placed. Okay, so as shown here, this there is 3 electrodes connected with this sensor, and this one is the this one is T connector embedded to added to the breadboard, and these input are fed to this Raspberry Pi. This one is a Raspberry Pi. This laptop is just used to view. Actually, this Raspberry Pi needs the output, but separate display. So we are using this laptop device just only as a display device, not as a computing device here. Okay, so this one is a virtual with this one is connected by a virtual LAN is there. So this provides the view of the this Raspberry Pi. Okay, so there are this green light, blinking green light is the pulse sensor. Okay, so multiple sensors are connected with this breadboard. So this Raspberry Pi needs the power supply. So this white cable is for the power supply, and there will be ground signal. Each sensor will be ground, power supply, and output connector will be connected to this input output T connector. Okay, this one is the description of the waveform. So I think we have to skip this waveform. Actually, we have the limited time, and we will not be able to cover the entire the classification of this waveform and so on. So I think it's better to skip this. Okay, so this one is just glimpse, like these are different types of segments of the waveform. So there will be time interval, and so with the basis of the time interval, these waveforms are analyzed. Okay, so this one is the directory format, how the smart contract, how we write the smart contract and add to the blockchain. So we have to write a smart contract. So contracts folder contain the health.sol file that contains our smart contract. Then health.test.js. This one is used for the testing purpose. If you are using Mocha or Chai for the testing, so these are the testing framework to test the smart contract. And if you are using the Remix ID, then there is no need to use this this Mocha and Chai. Directly with the help of Remix, you can test your smart contract. If your smart contract is working properly, then directly you can compile the smart contract, and the script for the compilation is written in the compile.js, and the script for the deployment to the blockchain network is written to the deploy.js. And this package.json file contains the configuration files or the dependency files that is used to deployment and compilation of the smart contract. Okay, so these are basically scripts how to run this, how to set up our project. So first we have to start the npm, then we have to install the Solidity compiler. And with the help of compile.js, this compile.js has the path of our smart contract. So when we write node compile.js, it starts the compilation process. Okay, then with I if already the smart contract is tested with the Remix ID, then there is no need to install the Mocha, and then no need to test it with the Mocha. Okay, and then we can deploy it directly to the either to the Ganas or to the uh, uh, Remix ID, to the original test network blockchain network, with the help of MetaMask. Okay, so Ganas is again works as a local test network. So there will be provider with the help of that provider, and there will be Web3 that will interact with the blockchain. Web3 is the framework to communicate with a decentralized application. So with the help of this Web3, we will with the help of this Web3 and this local Ganas network, we will initiate the transaction. Okay, so again the diagram is the same diagram. Our node will be a Infura works will be as a Infura node. Earlier diagram was based on the Ganas network, so there is no need to. Ganas itself provides the API, and in Ringp network, if you use Ringp or any test network, so you need any API Infura node that will work as a mining node or real-time node that participate in the mining process. So here we are working as a Infura node. Okay, so Infura, with the help of Infura node, we will pass our account details, and with the help of Infura node, we will communicate with the blockchain. Okay, so these are the after that we will deploy our smart contract. This one is the output, the balance of account. We are feeding our data from the account 0. So user may contain multiple accounts, account 0, account 1, account 2, account 3, and so on. So we are 1 minute please. Hello. the smart contract. So this one is the balance of our account contract, smart balance of our account zero in that particular test network. We are deploying this smart contract from account. This so from account is the account address of the user, and contract deployed to, that is the address of the contract address. Okay, so when next time when the user feed up the data to this smart contract or communicate interact with the smart contract, so this two address will be used. That is the address of the smart contract where the smart contract is deployed in the blockchain. Okay, so Rinkby, we can check our details on the global platform. Etherscan is the portal that provides us the different that provides us the different um, test networks. That is a public explorer from which we can check out our data publicly, what has been stored here, what has been stored. Okay, so this one is the Etherscan ring B. So in which the contract is deployed from A719 so on, and to C8. Okay, so this one is a contract creation. So there will be one contract creation and contract communication with the data feeding to the blockchain. So this one is the contract creation. So out from this one is the transaction has from account A7. Okay, so the user address, the address of the user is A7. So from this user address, the transaction is contract is created with this transaction fees. Okay, so next is there are several Geth provides us. So I'll give you basic idea how we will work with the Geth. So Geth is a Ethereum setup of blockchain, that is Go Ethereum. Geth, that is Go Ethereum. So there are multiple mining algos here. Although we have not discussed the mining algos, either proof of work or proof of authority, proof of stack, delegated proof of work, and so on, or delegated proof of stack, so on. There are multiple mining algos. We have discussed here only proof of work mining algos. Okay, so that is resource extensive proof of work mining algo. Okay, so the installation, we will first install the Geth node, and then after the installing the we are using here proof of authority. This one is one more simulation of our model. So earlier was based on the ganas and was based on the remix id. So this one is third setup, that is based on the Geth. Okay, so you can use any of the setup. There is no need to always use the Geth. The Geth is not mandatory for the testing purpose. Remix id is the, I think so, remix id with metamask is the best solution for starting with the blockchain deployment and compilation. Okay, so this one is the algorithm for this one is the algorithm where we are collecting the ECG data and storing this data to the blockchain. So the major issue with the blockchain is like when we initiate any transaction, then we have to pay the fees. We means user. When user initiate a transaction, then user has to pay the fees for that transaction. Okay, so if we store large amount of data, if we generate large amount of data and we are willing to store that large amount of data to the blockchain, in that case we have to that much amount of transaction fees. So there is the scalability is major issue in the blockchain. So the data should be the data set should be lesser, or will be, or should be less in the size. Okay, so so data should be lesser and less in size. So we have to compress, either we have to compress our data, or we have to use any mechanism by which we can say only the essential data or the required data. So for example, if we are storing the pulse, and if I storing the temperature of a human body repetitively after every second, so in 1 second there will be one instance will be generated. So what we can do is like storing the temperature after 1 minute or 2 minutes or 3 minutes, or we may use a mechanism like, if there is change in the temperature, if there is the time change in the temperature, only in that case we will store the data. So we have to find out any specific mechanism by which we can reduce the data. So ECG, in the ECG waveform, basically some parts, in some ECG parts, some waveform is a straight line. So we can reduce those points if there is no change in the ECG waveform. So we can reduce then those points, and we simply we write the occurrence of these points, because ECG waveform is captured after a fixed time interval. It means if ECG waveform is 360 hertz, then within 1 second 360 sample 360 amplitude value will be taken. So if there is a straight line kind of value, then we can skip those values and directly store the point and then the occurrence of those points. So one data compression mechanism is introduced that reduces the size of the ECG points. So this one is the sample example with the 360 hertz frequency. Okay, so this one is of 3 seconds. Sorry, this one is of 10 seconds data. Okay, so in 10 seconds there are roughly 10 spikes. On an average, we consider it at like 72 bits per second. Like, so there will be 12 waveforms in 10, 12 wave QRS waveform in the 10 seconds. Okay, so that will varies according to human body. Okay, so if the pulse rate is higher, then this frequency, sorry, this QRS waveform, occurrence of QRS within 10 seconds will increase. Okay, so analysis part will be the next part. So okay. So this diagram shows here like the transaction is deployed from the smart contract. Sorry, the transaction is contract deployment type. The smart contract deployment from the sender to this account address. There is transaction cost, how much transaction cost we have to pay, and then execution cost, and the status is contract deployed. Okay, so there are some security associated with this Ethereum blockchain. Okay, so immutability, reentrancy attack, integer overflow, DOS, fraudulent transaction, and transaction uh, auditability. So this one is integer overflow. So integer overflow means there is particular range of the integer. So there is particular range of the integer. So when this value goes beyond this range of the integer, then again set to the zero. So similarly to the C programming, where the integer underflow or overflow lies, similarly in the Solidity itself, there is integer overflow problem. So there is again one math header file. By using that, you can avoid this integer overflow problem. So reentrancy attack is like if there is any smart contract that if there is loop in the smart contract, then reentrancy attack can be happen. Is like uh, if a function calls iteratively itself without updating the value, and so this can be harmful for our model. So the code must be written in such a way that there should not be any there should not be any reentrancy in the earlier contract that is communicating. If two contracts are communicating with each other, then the, there should be proper check to access the smart contract. Okay, so with the placing the lines at the proper place, we can solve this reentrancy problem. Okay, so these are the publications, or like uh, we have also published one patent on this blockchain model of this blockchain technology with the IoT based IoT based blockchain technology for securing the IoT healthcare data. And we have one relevant to with this, we have written one journal paper that is fuzzy based vaccine distribution using blockchain technology, in which distribution of the vaccines are vaccines are done with the help of blockchain technology. There were some IoT sensor which were collecting the IoT data, which were collecting the real-time data and storing to the blockchain technology. Okay, some more e-voting system, and there are multiple other research papers are there related to this blockchain technology and the application of the blockchain technology. Okay, so these are the references these are the references for our blockchain. Those are used in this entire talk. So if you have any doubt, you are open to ask any doubt. So I request you, the host, to give the right to ask the question to the participants, or you may write directly your doubt to this chat box if you have any doubt related to this. So participants, if you have any doubt, you may ask. I'm not getting any response. Either I'm connected or not connected. I'm not sure. Like, I request the host team
The
to.
number you have dialed is currently busy.
Thank you, Himadri, and thank you, Chandni. PPTs will be provided to you after the completion of each and every means completion of this FDP. I request you to host to manage accordingly. They will share you this PPTs with you. So for when there is one doubt from Gaurav Kumar Das, that is how to start with the blockchain technology and which tool is comfortable to start with. So if you are working with the Ethereum blockchain, so first you have to learn how to write the smart contract. So for this, Remix ID is better, in which Remix ID is generally basically one online tool in which you can write your smart contract. First you have to try to write basic smart contract to store any data and to retrieve any data. Okay, so there will be GUI panel also within this Remix ID, from which you can show what is going on, what is the transaction fees, how the transaction is going to store in the blockchain technology. So after, when you are comfortable with the writing the smart contract, then you can deploy that smart contract to the test network. So MetaMask will provide you the MetaMask is a plugin that will provide you to deploy your smart contract to the test network. That will be like you are working with the real blockchain. When your setup is completed, means return of the smart contract is completed, compilation deployment is completed, and deployment to the test network is completed. After that, you have to go to your real time application. Yes, there is one more popular tool in nowadays, that is Hardhat. So using the Hardhat, you can set up your own blockchain network. Yes. Anything else? So Hardhat, you have to download the Hardhat. There is an installation guideline on the Hardhat portal itself, and there is also documentation is given there. So you have to download Hardhat, complete Hardhat package, and then you can write your smart contract and you can deploy your smart contract with the Hardhat also. So Hardhat provides you the environment. When you work with a Remix IDE and a MetaMask, that is completely online. You are working with the online manner. When you work with the hard hat, so you work on your own system. So your own system will work as a mining device, also as a node who initiates the transaction. So you can create your own private blockchain also. Hard hat is one framework. Chandni, is this clear? Thank you. Is any another doubt or any query? So you all may reach out at jitendra.goyal at bitmeshra.ac.in. I have texted you my mail ID. So you may reach out me if you have any doubt, or feel free to contact me on my phone regarding any doubt. Okay. So anything else? So I can understand this session is very lengthy session and exhaustive session for you. So sorry for that. Now I request the host team to continue the session.
Oh, okay, sir. So I thank Dr. Jiten Goel, sir, for delivering such an insightful and engaging session today. Your expertise and clear explanations have truly added great value to our FDP. And
Thank you.
thanks to all participants for making this session a success. So now we will be taking a break for 40 minutes, and we will meet again at 1:50 p.m.
Thank you, sir.
Thank you, sir.